Hey guys, imagine a disaster situation that's so dangerous we can't send people in to fix the problem. So what do you do about that? Well, this is RoboSimian, and that's exactly what he's designed to do. We're going to talk all about that on this episode of Crazy Engineering. All right, guys, we're here with Brett Kennedy. He's leading the charge here on the RoboSimian project. Hey, Brett, could you just tell us a little bit about RoboSimian? What were you guys trying to accomplish with the robot?
RoboSimian is actually a line of limbed robots that we've done here at JPL, but specifically it was designed and built for the DARPA Robotics challenge. It's disaster response, not life-saving. So the exemplar that DARPA uses is the Fukushima nuclear reactor. After the earthquake and the tsunami, there was a lot of damage to the reactor, and they really needed to be able to get inside and do a few things that would have made everything better. And it could be as simple as flipping a switch or turning a valve.
So JPL is kind of known for making rovers, and everyone knows that rovers have wheels and we kind of climb over rocks. Why did your team decide to go with limbs instead of wheels?
If you can get away with wheels, wheels are great. They're the most efficient way of getting around. But once you get into terrain that's too rough, then we need to switch over to a different method.
So how does the robot know where it is and where it's going?
So if it can, it's going to use its perception systems, its cameras and the LiDAR to actually build this 3D map. And it sends that information back to the operator. The operator then decides where it should go. But even if it doesn't have good data about what its environment looks like, it's also got force sensors in its wrists and ankles. So it can actually feel the terrain as it's walking as well. So we have the capability of basically moving around by braille.
So what exactly can it do?
Given the fact that it's sort of human scale, we can have the robot do a lot of things that a human can do actually, as long as you're not too concerned about it moving fast.
What kinds of hands or end effectors can you put at the end of these limbs?
We went through a couple sets of hands, and this is where we've ended up today. It's not for dexterous manipulation of things, but it can do most things you need, which is to grab onto objects, be able to pull them with a lot of force, and also manipulate certain things, and in particular, human tools.
So looking at this arm, it looks pretty advanced actually.
This limb is actually very similar to yours in other ways, particularly in the number of joints it has. So even though it doesn't look like it, it's actually about as dexterous as your own arm.
You've got 7 joints, I'm assuming 7 independent motors. Can you tell us a little bit about these motors, what torque capability they have, how fast they can go?
In every one of these joints, we have exactly the same drivetrain. This contains the electronics that run it, the brake, the motor itself, and the drivetrain, which is a harmonic gearing in this case.
What's your gear ratio that you're getting out of that harmonic drive?
160 to 1.
It's a pretty tight package, really high gear ratio.
Yeah. Out of this one little thing, we can actually get as much torque as an F-150 truck.
So I'm imagining RoboSimian kind of crawling its way through buildings and over difficult terrain, and that's all happening here on the Earth. Is it even possible to send this to space?
Well, the exact technology that goes into that would be different than what we have in RoboSimian today. The basic robotics problem is the same, and so yes, absolutely, we think to send these to the cliffs of Mars, to the outside of asteroids or comets, things of that nature.
All right, we're all wishing the best for the RoboSimian and the DARPA Robotics Challenge this June. Good luck out there, buddy.